Okay, what I'd like to do is this is an example of F equals MA. I wanted to do it in class, but we probably didn't have time. But since I'm homesick, I figured I'd record a couple extra videos for you. This is an example that I've done in past classes. We're out of time. Anyway, here we have a car, the infamous Gremlin with the YN 671 blower to the right, and it's going to travel 400 meters. And we want to know, based on the force, which is just strictly friction, and the mass, 1,225 kilograms, and the drag, which is given as 0.575 v squared, what is the maximum theoretical speed that it can reach in that 400 meters? All right. So first thing we're going to do is make sure you can see the screen. So here is our drawing. So here's the gremlin on the right and on the left, I'm sorry. And so there's the drag force that we're given. So we know that D is 0.575 times V squared. All right. And we're given that the friction coefficient is 0.7. Now, you might, why are we using the static coefficient? Because it's not sliding, the wheel is rolling. And so this coefficient of friction accounts for the fact that as the wheel rolls, essentially we're pushing the earth back and the earth is pushing the car forward. So our only forward force in this problem is the force of friction, which is going to be essentially the normal force acting on that wheel times its friction coefficient. Now we're told in the problem statement that the weight distribution is 62% in the front, 38% in the rear. We're going to assume that this is just free rolling, no friction. And the friction on the front is not rolling friction, it's the friction created to propel the car forward. So for example, if we were on ice, the wheel would just spin. So that's how it's performed in this class. And then, so that's our FBD. And of course, let's add weight. So weight. And then we have our mass acceleration diagram on the right, which is just MAX in the X direction. So let's figure out what our weight is. So we know that weight is equal to just mass times gravity. So if we multiply 1,225 kilograms by 9.81 meters per second squared, so we get 12,005 newtons. Now, that leads us to the fact that our force is going to be essentially the mu times n, right? So mu times normal force at the front wheel. So I guess we can call this A, this B. We'll say that's NA. So what that gives us then is it's essentially equal to 0.7, and then times what's the normal force? It's going to be 0.62 times the total weight of 12,005. So that essentially gives me a force of 5210 newtons. So that's the force that's pushing me forward. All right. So now I just set up my equation. Sum of the forces in the x equal mass times acceleration in the x. So I know that the sum of the forces is going to be F minus D, right, equals MAX. So that's going to give me 5210 minus 0.575 V squared. And that's all equal to the mass, 1,225 kilograms. I'll put that in there, times acceleration. Okay. So remember, we know that acceleration is equal to v dv dx. That's the relationship we learned the first week. So what we'll do is we're going to move things around. For one is we're going to substitute v dvx for that, and we're going to manipulate this a little. So we're going to set up our integral to be 0 to 400, and we're going to move dx over here to this side. So that's just coming over to the other side. And then we're going to set that equal to our v dv, and that's going to be divided by 5210 minus 0.575 v squared. And that's from v naught to v final. All right, so there's our integral. So now it's just a matter of integrating that. So, so for one, let me think. Oh, I did leave out this, the 1225. Sorry about that. So yeah, so essentially I just swap sides with everything. So dx over 1225 equals vf over that, over that. All right, and now we just need to solve it. So upon integration, we get 400, 0, and then that's just going to be, actually, oh wait, let me back up. Yeah, so to simplify this, what I'm going to get is x over 1225 evaluated from 0 to 400. And that is going to equal 1 over 0.575 times 1/2. And then that's going to be the negative log of 970 minus v squared, evaluated from all that in the box, 0 to v final. Okay. So using reintegrate there to there, we remember that the natural log of x plus y is the same as the log of x plus the log of y. That's part of what we did. Same with if you have the natural log of x minus y, natural log x, natural log minus y is the same as the natural log of x over y. So using these relationships, we were able to manipulate this, and we end up with 400 over 1225 equals 0.8696 times natural log of 970 minus v final squared plus natural log of 970. All right. So we end up with essentially 0.3754 equals log of 9070 over 9070 minus v final squared. And then take e of both sides, solve, and you end up with a velocity equal to about 53.3 meters per second, which is about 120 miles an hour. Okay. So really the F equals MA part was up here where we would set it up. We just need to identify what's what and identified our net force. And then we got to the rest of this, which is calculus. Now, this is more homework stuff. This isn't stuff on a test or a quiz, because if I don't want you to not get it right because you forget some your integration techniques, which should be better than mine. But as far as this stuff goes up here, you should be able to set it up. All right. So hopefully that helps you. Let's go ahead and do another example. So we did this one in class. And actually, hold on a sec. There, the beauty of pause. So here we have a problem. This was one that I'd done in class also. This was similar to the one where we had the carnival ride where people were spinning in a circle. And in this case, we have something a little simpler. You have a parabola-shaped dish, and you're given that you have a 2-pound ball of solid gold. It doesn't matter what it is. It's at rest relative to the parabolic dish, which rotates at a constant rate about a vertical axis. So we want to know the velocity of the sphere and the magnitude of the normal force exerted by the sphere on the inclined surface of the dish. So actually, that was something I realized now. This wasn't the problem I wanted to do. Hold on. Okay, sorry about that. So here's the problem I meant to do. I just written the wrong one. So here we have a 3-kilogram sphere of solid gold. Could be a sphere, could be a block, doesn't matter. So imagine that the whole thing is rotating and the sphere is in a single place. So it's not rolling, but it's friction that's holding it there, keeping it from going up or down. So we want to know at what point, how fast can that ball go? And again, that's tangential velocity. So essentially the ball relative to the dish is 0, but how much tangential velocity can it take before the ball will effectively roll up and out? All right. So here we have it. So what we're given is here is this. We're going to assume that it can be a ball square. It doesn't matter. And so now we have y equals r squared over 4. That's going to be the equation for our parabola. We're giving v static is 0.5, and it's a 3-kilogram ball. All right. So first thing we want to figure out is what is the slope? So the slope of dish. Well, we know that that's just going to be dy dr. So dy dr of r squared over 4 gives us 1/2 r. So our slope, or dy dr, gives us 1/2 r. Okay. Now we know that, and that's because we're trying to place this in here. We also know that if it's at 2 meters, then r equals 2. That means that this equals 1/2 times 2, which equals 1. Okay. But we also know that tangent theta also equals rise over run. So if the tangent of theta equals 1, then we know that that only occurs when theta is 45 degrees. Okay. So we know that's at 45 degrees. So now we're going to draw our free body diagram. So that'll look like this. All right. And so we're going to go ahead and use a y n. So there's n, there's y, like we did in class. So we know that the block, we'll just say it's a block for simplicity, mg, and normal, and of course friction, right? Because the block, what it wants to do is it wants to slide up and out, which makes sense. So you have that, and then that is going to equal everything mass times acceleration n. Okay. So let's go ahead like we did before. We're going to sum the forces in the y to 0, n cosine theta minus mu static n, which we're substituting for friction, sine theta minus mg equals 0. Okay. So we solve, and we know that's 45, that's 45. So essentially n gives us 3 times 9.8 seconds squared, and this is kilograms, and that's all divided by cosine 45, which is square root of 2 over 2, minus 0.5 sine 45, right? And then so n is going to give me a value of about 83.15 newtons. Now what I'm going to do is I'm going to sum my forces in the n direction equal to mass times acceleration n. So if I do that, I get n sine 45 plus mu static times n cosine 45 equals mass. Now we know acceleration n is equal to what? V squared over rho. So m v squared over rho. All right. So essentially now we have everything. We know the mass. We know that's 2 meters. So we plug in 83.15, and our final, we get 83.15 times root 2 over 2 plus 0.5 times 83.15 times root 2 over 2, all divided by, 3 kilograms. And then all of that times 2, which is the radius, 2 meters, and that equals v squared. Okay, so my v then is equal to 7.66 meters per second. All right, and that's that. Hope that helps. There's the top, and you can always rewind. So hope that helps, and I'll post the next video, which will be the actual lecture. Thank you.